Hello, this video is entitled Series and Convergence. Now let's talk about what a series is. Sort of relates to the idea on sequences, but to make a series, we're taking each term of a sequence and we're adding all those terms together. So this is a Greek letter, upper letter sigma, and n equals 1 to infinity of a to the n means a1 plus a2 plus a3, so forth and so on, and we call that an infinite series. So it's because it's going to infinity, it's never going to add up to an exact value, so we'll use the same terminology as we did with sequences, and when we say converging to a certain value, or of course it may diverge. Now let's look at this particular series here. In fact, the section on sequences, the rest of this chapter is going to pretty much be on series, so we have to make sure we're clear on the distinction between a sequence, which just lists the terms out one after another, versus the series, which adds those terms. Well, this is not the way you would actually solve this particular problem. This is just sort of an illustration. Suppose I took 1/2 to the n equals 1 to infinity. Now I'm making this a 1 by 1 box because I know that the answer is going to be 1. So that's why this would not be a very good. Well, it's almost like you have to know the answer before you do it. But so if I start out the first term, I put 1 in there, it'd be 1/2. So I filled in the space for 1/2. And then the next term, you put 2 in there, it'll be 1/4. And then 3 will be 1/8. So what happens is you would keep filling this box up, and then you'd have 1 over 32nd, 1 over 64, over and over and over and over. You know, theoretically, you would never fill it completely up, but it would get so close to being full that it might as well be full. So we would say that it converges to 1. And that's what Maple just doesn't put the terminology converges in there. So when I say almost filled up here, I mean just infinitesimally close to being full. All right, but that's not how we're going to solve these, but that's just sort of a visual explanation of why that one would be 1. Now I'm going to briefly explain this partial sum idea. That's not the way we're going to technique we're going to specifically use. But let me, I think it's good to talk about what this means. As I said, it's not all that practical to use. So partial sums would be taking sums of adding, certain terms at a time. So the first partial sum, S1, would be the first term, A1. S2 would be A1 plus A2. S3 would be A3. A1 plus A2 plus A3, all the way to Sn. So what we have now is a sequence of terms. This is what would be a sequence of sums, and then if that sequence of sums converges to some value S, then the series will converge to that S. Otherwise, it would diverge. But this, like I said, there'll be a much better way to evaluate this. But anyway, so here's what it would look like for this same example. S1 would be 1/2. S2 would be 1/2 plus 1/4, which is 3/4. Next one would be all three of them added together, which is 7/8. That's adding, let's see, 1/8 would be the third term of the sequence. I didn't just think of the terms being 1/2, 1/4, 1/8, 1/16. So I had 1/8. We're not working off this. That's the actual result. So it'd be 1/2. So this is 1/2 plus 1/4 plus 1/8 is 7/8. So I'm just taking this total each time and adding the new term. Next term would be 1/16. So this is the sequence of the partial sums, and it goes like this. Now this might be a little tricky to come up with that formula, but anyway, so the idea is the limit of the sequence of the partial sums gives you what the original series would converge to. So the limit of these sequence terms equals 1, so therefore the series will converge to 1. Not real practical, but theoretically it's an interesting idea. Now we're going to look at two special types of series in this section, and there'll be more as we go throughout this chapter. First one's called telescoping. Telescoping is two fractional terms that have minus between them. So for example, this would not be telescoping, and it would be kind of easy to figure out that this was not going to converge, because if you're adding terms, this plus the next one plus the next one, it's just going to keep growing and growing. So the only chance that this has to converge is that you've got some, minus terms in there. So that diverges. So as long as this is subtraction. Now let's see how this, and then they're always going to converge. Because one of the big issues in this chapter with series is determining whether or not they're going to converge or diverge. Now, as long as it's telescoping by definition with the minus, it will converge, but we're actually interested in figuring out what will it converge to. So what I'm going to do is just kind of list out a few terms, and I'm going to show you a trick here in a little bit to kind of speed up the process. But it's good to list these out, and even if you kind of forget the trick, you can still always come back to this. It wouldn't be that, complicated. I'm going to put 1 in here, into this series. So I have 1 over 1 minus 1/2. So I don't add those together, leave it like this. Plus, put 2 in there, 1 over 2 minus 1 over 3. See, I wrote the ends right below it. For n equals 3, 1 over 3 minus 1 over 4. And then we have 1 over 4 minus 1 over 5 when n equals 4. Now notice that, that we got some things that will cancel, like this negative 1/2, positive 1/2, negative 1/3, positive 1/3, negative 1/4, positive 1/4. But you see that you're always going to be left with a term kind of hanging here on the end. That's actually not going to be a problem, because what happens is, as this goes larger and larger towards infinity, this term right here, which is basically 1 over n plus 1, that's going to converge to 0. It's not going to actually equal 0, but it's going to essentially go to 0, like I wrote right here. So it's going to fade away as far as the sum goes. So you can ignore all these trailing terms at the end. They're not going to affect anything. What's going to affect the sum is the one. Sometimes there'll be more than one term, and I'll tell you how to tell that in a minute too. But whatever that isn't going over anywhere. In other words, that 1 over 1 was not going to cancel. It's there. You see how they cancel, but then, so this one fades away. The 1, so you add up whatever remaining terms are there. So only have one term is 1, so therefore this telescoping series will converge to 1. And Maple also agrees with that. Fantastic. Now here's one where you've got to do a little partial fraction decomposition. But the good news is, if you ever have to do this, they're going to be the easiest case, which is the distinct linear. So it will not be hard to have to break that down if you need to. And maybe you have to factor the denominator first even or something, but this one's already factored. So I have a over n plus b over n plus 2. And then, of course, we clear out the denominator. So I have 4 equals a times n plus 2 plus bn. So when n equals 0, I have 2a equals 4, so a is 2. And then for negative 2, that wipes out a. I get negative 2b equals 4. And b equals negative 2. And then now this is our series right here. So it's 2 over n. It's got the required minus that we need. So that's what guarantees it's telescoping. Minus 2 over n plus 2. Now, two ways you can approach this. Yes, you could factor out a 2 here if you wanted to. But you would have to remember that if you factored out a 2 and whatever terms are left here, you're going to have to multiply it by that too. So as long as you remember to do that, you're okay. So in this case, I'm just going to leave the 2 there. I'm not going to worry about factoring it out. That way I don't have to worry about multiplying at the end. There may be an example coming up where I do factor it out. But you have complete freedom to do it whatever way you want. So once again, I'm going to list out some terms here. This time I kind of went all the way to n equals 5 this time. So you put in 1, 2 over 1 is 2, 2 over, minus 2/3. Put in 2, 2 over 2 is 1, and then 2 over 4 would be 1/2. Put in 3, you got 2 over 3, minus 2 over 5. Put in 4 here, you got 1/2. 2 over 6, minus 1/3. Put in 5, you got 2 over 5, and you have minus 2 over 7. So I'm stopping right there. Now you can see the minus 2/3 cancels out with the plus 2/3. The minus 1/2 cancels out with the plus 1/2. The minus 2/5 cancels out with 2/5. Well, in this one, we're always going to have 2 trailing terms. That will never cancel. But guess what? All those trailing terms, whether there's 1, 2, 3, however many, they're going to go to fade as close to 0. So we can, just because there's 2 now, we still are fortunate enough to be able to completely ignore them. So we go back and look at the beginning. So the beginning is what's going to determine what your answer is. All these terms fade away. I have a 2 that wasn't going anywhere, and I have a 1 that wasn't going anywhere. So all I have to do is take the 2 plus the 1, add them together, converges to 3. And here's where I mentioned the last 2 terms. We'll approach 0. Maple says it's 3. Now let's see. Yeah, I didn't know if I wrote it out or not, so I'm going to say it verbally. Here's my shortcut rule I was telling you about. That the number, so your answer is always going to come from the first terms from each of the first sets of parentheses. Could be more. Next example is going to be more than 2 even, but they're always the first ones. So what you do is look at the difference in the denominators. See, the last one there was a difference of 1, I believe. We go up here. It was n and n plus 1, so the difference was 1. This one, it's a difference of 2, n and n plus 2. So that means I'm going to keep 2 terms. That's going to be the first one from the first parentheses and the first one from the second parentheses, and add those together. So the quick way is, once you get this 2 established right here, and once you get that 1, it's game over. You just add those together, and that's your answer. So that's kind of a quick and convenient way to get that, I think. Much faster. So once I have the 2 and I have the 1, I add them together and I get 3. So like I say, the last one was only a difference of 1, so we just had the first term remaining right there. Isn't that exciting? Oh, okay, so that's where I just explained how to do it. Here I wrote it out for this particular example, the shortcut. Let's see this one. So you have an n and n plus 4. So the difference is 4 between those 2. Now that one's already factored for us. I mean, it's already partial fraction broke down. So yes, I wrote out all this stuff here, but I didn't need to. All I had to do is establish what was the first term in the first 4 sets of parentheses, because of that difference of 4 right there. So really all you're doing is evaluating this term right here for n equals 1, 2, 3, and 4, and adding them up. So that's pretty quick and convenient. I like that. So of course 5 over 1 is 5. 5 plus 5 halves plus 5 thirds plus 5 fourths. Now you can use a calculator, but I went ahead and just got me a nice little common denominator of 12. And adds up to 125 over 12, which is exactly what Maple says it is. How convenient. So there's a quick way to get through telescoping series. Oh, looks like we got another one. Hopefully this will be the last one. Yeah. Just so we can move on to something else. All right, n minus 2, n plus 1. A little trickier here, but it's a difference of 3. There's a difference between negative 2 and positive 1. So I would use, and always pay attention to where your series starts here. They don't have to always start at 1. You'll see that come up throughout certain ones. This one's starting at 3. So, don't get in the habit, and glad I did that now because of automatically just plugging in 1 the first time. Your series starts at 3. Now, this one, they didn't do that to trick you, but this was done out of necessity. I say they. Actually, I created this example, but it wasn't done to trick you. But we could not start this at 1 or 2. Because 1 would be okay, but as soon as you hit 2, you've got divide by 0. So that would be a problem. So you'll see other series that do that too. But this is, I just started at 3. So I put 3 here. 1 over 3 minus 2 is 1. 1 over 4 minus 2 is 1/2. 1 over 5 minus 2 is 1/3. So I add 1 plus 1/2 plus 1/3, and I get 11 over 6. And Maple seems to approve of that answer. All right, let's talk about a geometric series. Geometric series often start at 0, but they don't have to. We're going to address that issue too when we start at something other than 0. But a geometric series is a series where each term is a multiple of the prior term. So R is called the common ratio or the common multiple. A, R to the n, so you put 0 in there, R to the 0 will be 1. So you have A plus R, A times R plus A times R squared plus all the way to A times R n. So this one, 1, 1/3, 1/9, 1/27. Now it's real easy to get the common ratio if you're just given a list of terms like this. And what's the common ratio? You take any term and you divide it by its previous term. That's going to give you the common ratio. Now here's one that's just a doubling sequence. So that has an R of 1/3. This goes 1, 2, 4, 8, 16. So each term's doubling. The multiple would be 2. Now this, we have to determine whether or not a geometric series, now I just wrote this out because of this, called that a sequence because we're just listing the terms out. But now it's a series because we're trying to find the sum of those terms. Basically, R has to be between -1 and 1 without including -1. So that's the same thing as saying the absolute value of R is greater than or equal, just the opposite of that, R greater than 1. So R has to be between -1 and 1 without equaling -1 and 1 to converge. Any other value of R will diverge. And here's the formula, which when you start at 0, we're going to talk about when it doesn't start at 0, but it starts at 0, n equals 0 to infinity, a r to the n. The sum of that geometric series will be a divided by 1 minus r. All right, so let's take a look at some examples here. Now here's one so I put in 6 times 1 plus 1.1 raised to the n. Well, that series diverges because that r is not between -1 and 1. I don't know what this float means, but that infinity that Maple has right there, that's enough to make it diverge. But notice this one, 0.999, whatever, that's less than 1, so it's going to converge. And in fact, that one would converge to 6,000. So negative 0.99 would have also converged, 0.999 or whatever. Oh, and there's the formula. So it'd be 6 divided by 1 minus 0.999, which is 6 divided by 0.001 equals 6,000. So it's pretty straightforward on telling whether or not it's going to converge. And it's very straightforward on figuring out the sum when the n starts at 0. So we have negative 2/3 for this example. So we're in good shape. That's between negative 1 and 1. So had that been negative 3/2, we would have diverged. So the R is negative 2/3. So the A is 2. Obviously, if there's no number there, A will be 1. So it's 2 over 1 minus a minus 2/3, which is 2 over 5/3. And that converges to 6/5. Now, let's talk about what happens when the counter is starting at something other than 0, like 1. So you have to pay real close attention to this, because sometimes, I often will put this on a test. So you just don't want to jump right into the A over 1 minus R. We are going to use it, but that's not going to be the exact answer. Now, it's going to converge, so let me clarify that. It does not affect whether or not it converges. It's going to affect what the sum's going to be. So what you're basically doing, I'll say all this as clearly as I can in just normal word form here. But when you're evaluating A over 1 minus R, you're evaluating it automatically starting at 0. In other words, you have AR 0 plus AR 1 plus AR squared. It's giving you all of that. But whenever we start at 1 here, we don't want this first term. We just want it starting at AR 1 all the way to ARN. Okay. So what we do is we subtract off both sides, minus AR0 minus AR0. So that means then to do it for this one, starting at n equals 1, you just take the formula A over 1 minus R, so we still start with that. Then you subtract out what the 0th term would be. The 0 term would be, so that way then it will add it up from 1 all the way to infinity. It'll remove the 0. So you see, you subtract all terms prior to where n begins if n is greater than 0. Now, I rewrote this same part right here, but actually I didn't need to, but we'll just kind of pretend like if we were doing this from scratch. The reason why I said I didn't need to is because we already got it right up here at 6 over 5, but pretend like we didn't. So that would be starting at 0. It would be 6/5 minus, literally taking this term, the 0 term, or putting 0 in there. So it's minus 2 times negative 2/3 to the 0. So it's 6 over 5 minus 2. So this time it'll converge to negative 4 over 5. So watch where that counter starts. And I don't get anything, n equals 1. Maybe here's an n equals 2. I wouldn't go anywhere worse than that. I wouldn't try to torture you by starting it at n equals 10 or something, and make you have to subtract off a bunch of terms. 2 is good enough, I think, here. So from 2 to infinity of this same formula, we would take the 6 over 5, which is starting at 0, subtract off the n equals 0 term, now subtract off the n equals 1 terms. So you're just subtracting off all terms prior to where the number starts right here. So there's the same 2 from right here. And now we need to get this new number here. So when you put 1 in here, 2 times negative 2/3 is negative 4/3. So 6 over 5 minus 2 is negative 4/5 plus 4/3. Well, there it is right there. Anyway, yeah, it's those same part right there. And now add 4/3 to that, and I get 8 over 15. So needless to say, to kind of verify my results, I put this in maple for you to help you reassure that I wasn't just making up a bunch of nonsense there. But there they are. 6 over 5, negative 4 over 5. Look at the counters. 0, 1, and 2. And there's 2, 8 over 15. So it looks like I did it for some reason. I felt like doing another one starting at 2. Probably requested the student want to see another example, so no problem. So anyway, Now it's converging because it's 1/5 starting at 2. So I'll get the formula answer starting at 0 by doing a over 1 minus r. So 3 over 1 minus 1/5, 3 over 4/5 is 15 over 4, which that would be the answer if it started at 0. I need to subtract off the n equals 0 term and the n equals 1 term. So you see I wrote it right there. So minus 3 1/5 to the 0, minus 3 1/5 to the 1. So it's 15 over 4 from right here, minus 3 minus 3/5 is 3 over 20. And Maple says 3 over 20. That's wonderful. All right, now here's a new theorem for convergence of series in general relating to sequence. If a series converges, for example, if series AN converges, then the limit of the sequence, in other words, then if you just look at the individual terms, that's going to go to 0. Now you always have to be careful anytime you read an if-then argument, because it's if-then means it only works one direction. The opposite is not automatically guaranteed to be true. It can be true, for certain scenarios, but not by rule. Some of you, maybe if you're computer science and you take discrete math or something, you might learn a little symbolic logic or something like that, which frankly I would think symbolic logic would be good for anyone. But I wouldn't blame someone. I took it as an elective 100 years ago, but it was fun, I remember. So it's kind of using symbols and rules and if and ands and ors and trying to see if two different arguments were logically equivalent by using notation and stuff. But anyway, so in other words, if A then B does not guarantee if B then A. Now, we're going to learn. So you see the limit of this sequence, 1 over n, that would clearly be 0. You just put the infinity in there. Now that looks like it would converge, but we're going to have some rules to show why, so you're just going to have to accept it for now. But because it looks like it'd be sort of like the geometric, and because you're adding up fractions, but it does not. So if you take 1 over 1 plus 1 over 2 plus 1 over 3 plus 1 over 4, it does not converge. Infinity guarantees diverge. So there's an example of the limit of the sequence going to 0, yet the series diverged. Now, here's the reverse of this. If the limit of the sequence does not go to 0, then for sure the series AN diverges. So it's kind of like using this logical argument right here, because this is true in logic. Like I said, if A implies B, you can't say B implies A, but you can say this means not. Some books use this, the prime not, or they use this little thing they call it tilde in logic, but it means not. So it means not B implies not A. So the limit not equaling 0 means it not converges. So it's actually the logical opposite of Theorem 9.8. Now we're going to have a whole bunch of rules coming up in this chapter, reasons. Each individual rule is actually pretty easy to learn, but when you have about 7 or 8 different ways to determine if a series converges or diverges by what means, it can get a little confusing. We don't have much to work with right now. But here's an example of that theorem. See this series right here? This, right now we only know telescoping, geometric, and now we know the nth term test for divergence. The nth term test for divergence, let me come back up here for a second. Yeah, right here. Yeah, there is no nth term test for convergence. That only applies for divergence. So we don't know much yet as far as the number of different ways they can converge. We're not working with much information. But this one, because if you took this and looked at the sequence part only without the summation, if you look at that sequence, you can easily see, the n goes to infinity. I mean, without even doing L'Hopital's rule, you can see that goes to 2/3. Well, Last time I checked, 2/3 does not equal 0. So it guarantees that it'll diverge, and I just put it in there to show. You see there's the infinity, but that was not necessary. But since 2/3 right here does not equal 0, then you know it diverges by the nth term test. Now I like the way this book, this particular Larson Arthur takes, in this particular chapter, takes problems at the end, their end of the chapter, where they use things you've learned in that section or any other section in this chapter prior to it. So obviously the later on sections will have more examples. But right now we don't have much to use yet. So, okay, so this example, so we're looking at pretty much either nth term test, geometric, or telescoping. Let me see if I mentioned this in the notes. If not, I'm going to say it verbally. I probably have it also in another set of notes. I'll probably say this in the next section of notes, but let me go ahead and say this now too, that doesn't hurt. That the only series that we're going to care about what the sum actually converges to are telescoping and geometric. The rest of this chapter, we're only going to care if they converge or diverge and by what reason or reasons, because some of it would be far too mathematically complicated to figure out what it converges to, but the rules to determine whether or not they converge aren't that bad. So this is, so only telescoping and geometric will we be interested in their the value they converge to. Alrighty, so here's another one just like that last one. That limit goes to 4/3, diverges by nth term test. Alright, well, we've seen this, telescoping. I'll go through this a little bit quicker now that we've seen this. So you split it up, do the partial fraction decomp right here. Let n equal 0, n equals -3, solve for the a and solve for the b. And you end up with, it does turn out to be telescoping because it has the minus in there between it. So, see, minus is what makes it telescoping. And then if it's telescoping, it's automatic converge. So there won't be geometric series, it can still be geometric and either converge or diverge. But without the minus, it's not even telescoping. It's just some random diverging series, not telescoping. So we have 2/3 and -2/3. So you have 2/3 over n minus 2/3 over n plus 3. Now I mentioned earlier when we were doing this, you could choose whether or not to pull the constant out as long as you remember to multiply by it later. Well, I chose to do that for this example, probably because it was 2/3 and not some whole number. If it had been a whole number, I might have just left it there. So no rhyme or reason. You do whatever you want other than the rhyme or reason, making sure that you distribute it back. So I pulled the 2/3 out, 1 over n plus 3. Now I wrote out a bunch of stuff here, but let's use the trick here sort of that we learned. The difference between n and n plus 3 is 3. So it's going to be the first term of each of the 3 sets of parentheses. So it's 1 plus 1/2 plus 1/3, but we do have the 2/3 multiple out in front. Very important. If we didn't have that, it would just be these 3. But yeah, you're still adding those 3 numbers together like we normally would, but if you have that multiple out there, you have to take that into play. So I have 1 plus 1/2 plus 1/3 times that 2/3. It's 2/3 times 11 over 6, which reduces to 11 over 9. Maple says it's 11 over 9, so that's terrific news. Let's look at this example, 3 to the n over 1,000. See, that 1,000 can be pulled out, so it doesn't mean anything. 3 to the n, the common ratio r is 3. Game over, diverging geometric. I don't know if I would ask one this weird, but I thought it was kind of oddly beautiful there, so I thought I'd take a look at it. Now, e to the negative n is the same thing as 1 over e to the n. Now, 1's the only number we can do this. Keep this in mind, very important. Like if we had 5 over something, you can't make that 5 over n. But you see, I can rewrite 1 over e to the n as 1 over e all to the n because 1 to the n is 1. So 1's the only number that works that way. So if it was 1 over 5 to the n, I could write that as 1/5 to the n. So here it is, 1 over e to the n. So e, remember, e is a number. Obviously, you don't know what that number is, but it's 2.718, blah, 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 blah. But you can take 1 over e in your calculator, and if you weren't sure, and it's less than 1, so we do have a converging geometric. Now it's starting at 1 here, so that's important. I'll have to subtract off the 0 term here. So using the a over 1 minus r, I have 1 over 1 minus 1 over e minus 1 over e to the 0 would just be 1 right here. Okay, I got a common denominator here, e over e, so it's e minus 1 over e there, and then minus that 1 with 1 on top. This flips over, so it's e over e minus 1. Got a common denominator here for 1. I made it e minus 1 over e minus 1. And then the e's cancel. Negative of negative 1 is positive 1. So it's 1 over e minus 1, which is the same thing as the maple answer of negative 1 over negative 1 plus e. So that concludes this video on series and convergence.